Hello, Mr. Price here, and this is the final video for the January 2006 M2 paper, and this one is on question 8, and this one is a angular velocity question. Let's take a look. Now it looks quite intimidating, but it shouldn't be too bad if you know what you're doing. So our diagram speaks 1,000 words here. We know we've got a particle of mass 0.1 kilograms. This is important because it's not on the diagram, and it's moving with a constant angular speed of omega in this horizontal circle on this smooth inner surface of the cone. That's quite important. It's a smooth inner surface. Okay, so we don't have to worry about any kind of friction going on the cone, and we have a fixed vertex A at its lowest point. And we have an angle here of 60 degrees and a distance of 0.8 meters. And our first question asks us to calculate the magnitude of the force exerted by the cone on the particle. Okay, and this is just basically asking you for the reaction force of the cone on P. Okay, so with these kind of questions involving 3D angular velocity, it always starts with the same thing. We want to draw a simplified force diagram of our particle. So here's our particle on the surface of the sphere, of the cone. Now it's going to experience a weight of 0.1 g, and there will be a reaction force here of r. Okay. So first things first, I want to know what one of these angles are. Okay, resolving horizontally and vertically. So if I just do another diagram here, this might help. So I know that from the vertical, this creates an angle of 60 degrees. So if I've got a particle here that's the same thing, the reaction force is going to be normal to this angle here. So that this is also 60. So this bit here must be 40. Okay, so this bit here must be 40. So this bit must be 60. Okay, and these angles are going to be very important to us. Okay, and we know that it's travelling in a circle, so there's going to be an acceleration towards the centre of the circle, like so. Okay, now for part I, it's fairly simple, because if we look resolving vertically, we can see there's only going to be one unknown, which is the reaction force. So let's go and do it. So, resolving upwards, we have r sine 60 will equal 0.1 g. So the reaction force here must be 1.13 newtons. Okay, and that's for part I. Nothing to do with angular velocity yet. It's just what you did in M1. Okay, and it always starts like this, so don't be intimidated by it. Okay, now for part 2. We want to calculate the angular velocity, omega. Okay, so now that we know the reaction force, we can now resolve in this horizontal plane. So, resolving in the direction of acceleration, we know that r cosine 60 will be equal to ma. So substituting in our value of r and our value of m, 0.1, we have an acceleration value of 5.65 meters per second per second. Now we know the acceleration, we can start to calculate the angular velocity. So I know that the acceleration is equal to the radius of the circle multiplied by the square of the angular velocity. Now, I don't know the radius yet, so let's go back to my diagram. And I know that this distance there was 0.8 meters. I have this angle here of 60 degrees. So it's a fairly simple process now to calculate the radius. So I can see that the radius is going to be formed using sine, right? So sine 60 equals the opposite over the hypotenuse. So r here will equal 0.693. So substituting that back here, the acceleration equals 0.6, beg your pardon, we're trying to find the omega, we know the acceleration, 5.65 equals 0.693 omega squared. So omega, the angular velocity, is equal to 2.86 radians per second. And that's part 2. Now let's have a look at part 3. Looks like our diagram's changed a little bit, so we'll be sure to look carefully. Our particle is now attached to one end of a light inextensible string which passes through a smooth hole at A, so there's going to be no energy or force lost here. And this is an equilibrium with the string taut, and this is still 0.8 meters. And P moves in a horizontal circle with a constant speed still, and we want to state the tension in this string. Only worth 1 mark, so we know it's not going to be too tricky, and actually it turns out it's not. So let's look at particle Q, which was the one that was hanging freely. We know it's an equilibrium, and we knew that its weight is 0.2 g, so therefore the tension in the string must also be 0.2 g. So the tension there is 1.96 newtons. That's it for 1 mark there. Oops, sorry, you can't see much of that. So this is 0.2 g. The tension, it's an equilibrium, must also be 0.2 g, so tension was 1.96. Okay, and now finally, for part 4, we want to find the velocity of our rotating object. So let's do a new force diagram. Spot the pattern that's happening here. Force diagrams are so important. Okay. Put on my planes. I have a reaction force. I have my weight, 0.1 g. And then I have my tension, which is acting parallel to the plane of the surface. Okay, so this is parallel to the cone, so I know that this has to be 60 degrees, and I knew earlier that this was 60 degrees. And I know this tension, so let's resolve upwards first to get my new reaction force. Yes, I'm going to need that. So resolving upwards, because my reaction force is going to change here. So R sine 60 will be equal to 0.1 g plus T cosine 60. We know the tension there was 1.96. So the reaction force here is 2.26 newtons. Okay, and now we know all of the forces, so we can work out the new acceleration of our object. So now, resolving in the direction of the acceleration, we have r cos 60 plus t sine 60 is equal to ma. We know r, we know t, and we know m. So after some calculations, you should find the acceleration to be 29.372. Meters per second. So then let's go back. I'm running out of space here a little bit. So I know that A equals omega squared r, and I also know that the tangential speed is omega r. So that means that omega is v over r. So substituting in, A equals v squared over r squared, lots of r, so cancelling out we have A equals v squared over r. Now we know the acceleration and we know the radius of the circle, that hasn't changed, so after some substitution you should find that v is equal to 4.43 meters per second, and that is question 8 completely done, and I hope that helps.